Welcome back to DR Electronics. In today's video, I'm going to be covering the second part of my breadboard adjustable power supply. The first video covered in detail the parts I selected regarding the fuse, inductor, boost converter, its calculations, the incorrect setup I had for the feedback node and the feedback resistors, along with the LDO regulator and why I was making the supply in the first place, given that I want an adjustable output voltage along with a fixed 5 volts and a fixed 3.3 volts. This video is going to be covering the schematic changes I made along with the first initial layout, the problems that it had, and the corrections I made to it. For those who didn't watch the first part, here's a quick recap. Basically, the resistors that I selected here for my feedback system never allowed the output voltage to be higher than the input voltage. And this can be proven through the calculation of Vout given a boost converter. And that was seen in the Texas Instruments document that I showed in the first part. Not only that, but the Schottky diode was placed after the feedback system instead of it being in between the inductor and the feedback loop, seen with the 3 resistors here. So this was all that was wrong with the schematic in the first version. Everything else pretty much remained the same. So when looking at the new version here, we could see that there are some slight changes. So now the diode is moved so it's in between these 2 parts, and the potentiometer here, the wiper pin, is shorted to pin 3 of the resistor. This is so that instead of using the feedback pin here as a voltage reference, we are more so trying to use this resistor as an actual adjustable resistor as we initially intended, instead of just creating a high reference voltage here and thus not allowing the system to actually properly convert said voltage. So that, and I removed one of the resistors and placed an 8K resistor here. So again, everything else remained exactly the same in terms of part selection. Unfortunately, LCSC ran out of certain components that I was using, such as the LDO regulator, and I had to switch the Schottky diode, but their intended ratings in terms of voltage and current were exactly the same, along with their footprints for the most part, as I didn't really want to move too many parts around in the layout and make dramatic changes to such a small design such as this. So let's look at the first version of the PCB here. And for the initial version here, what I want to mention in particular that I find very important is the pin header spacing here is off by 4 millimeters. That may not sound like a lot, but in terms of actually getting this to fit on a breadboard, it is crucial that the spacing of the outer pins matches where the 2 rails are. Otherwise, you're going to have to bend the pins themselves in order for it to actually fit on the rails. So that was a first mistake that I made, because when I measured my Arduino breadboard power supply with calipers, I took an incorrect measurement down instead of checking it a few times, and I just assumed it was right. So when I made the board, I was quite surprised that it didn't fit, but given a new measurement, I found that it wasn't 43.7 millimeters, it was actually 47.4 millimeters. So that was the reason for this not fitting in the first place. And then again, because of the fact that the schematic is wrong, the way the layout is connected with the potentiometer and the Schottky diode is also wrong. As we're going to see later on too, I'm noticing that there's a slight issue with the boost converter's switching node in terms of the waveform output. It should be a square wave, but I am getting a square wave, but there's some noise and distortion, and we'll show that later on. But the overall layout itself was fine for the most part. You know, I have my USB-C connector with the 5 volts input. I have heavy traces or thick traces here for the power in terms of the jumpers, the input of the LDO regulator. This has its own copper pores along with the output jumpers here. And the boost converter itself, I tried to keep parts as close as possible. So the inductor is very close to the IC. The feedback system doesn't matter as much, but I tried to keep that close as well, so that way the copper pores weren't drawn out too far. And I have the top plane of this board acting for power and the bottom as ground. So there's no bottom traces, which means that the ground plane is completely secure. There's no cuts into it, which is good. And I have some test points here. I also forgot to label this test point here with V out. So if I wanted to test this board, I would have to go back to the schematic or layout to see what it actually is. Other than that, though, this board is very simple. You know, you just have your 5 volts input, you have a fixed 3.3 volts output, and you have an adjustable converter with a potentiometer that you set with a screwdriver. So there really wasn't too much to mess up here, but real quick, I'll just show you the newer design. So here I made a larger copper pore for the potentiometer. The layout for the boost converter really didn't change too much. I just adjusted the pores slightly so it included more of the parts. The trace width here stayed the same. It was about 1 millimeter. For everything else, it was about 0.8 millimeters, as again, we're mostly just dealing with power and not so much other signals except for the boost converter with the switching pin. So that's really the only concern we have with that, as we don't really want to induce too much noise with this, though given the fact that this is connected to a pin header followed by another pin header that goes into a breadboard, that may be some of the reason that I'm seeing some of the noise here. But if anybody has any further ideas into the comments, whether it be my layout or something that I overlooked in the data sheet, feel free to let me know. Also, another thing that I want to mention that I noticed in the actual data sheet of the converter itself was that the switching current limit of 4 amps is not tested. It's only guaranteed by design. So when calculating the maximum output current that the IC can withstand, this switch current limit is very important. Typically for a lot of ICs of this package, it's 2 amps, but this one's 4. So if I put it to 2, instead of getting about 1.1 amps of current, we can only get about 520 milliamps of current, or 0.5 amps. So that's a big difference. Again, unfortunately, I don't have the actual proper test equipment, like an electronic load, to simulate light, medium, and heavy loads for this, though we are going to try our best to see what we could get in terms of the output with the oscilloscope. So now I'm just going to show you the setup that I made for this, some of the tests I did, and the overall results that I gathered from it. Okay, so here's the setup that I have. I have the breadboard power supply tied to this mini breadboard here with the channel 2 of my scope tied to the ground, and I have the jumper on the left set at 3.3 volts with the jumper on the right set to 5 volts. So if we look at the RMS value here for the left side, we have an RMS of 3.2 volts, and for the right side we have an RMS of 5.2 volts. Now if I adjust this jumper to V out here and then measure it on the rail, we could see that we have an RMS of 14.4 volts. Now the reason why it's not 15 is because I used an 8.2K for R4 instead of an 8K, as that's all I had on hand. But if we take the screwdriver here and adjust the potentiometer counterclockwise, we could see that the output goes lower. And if I adjust it all the way counterclockwise, we then get a value of 5 volts. So essentially the resistance is close to 0 on the potentiometer here. But now I'm just going to set it all the way back up because I wanted to mention the switching node of the converter tied to the inductor, the right side here. If we take a look at it by probing it directly with our scope here, we could see that the switching frequency is 1.2 megahertz. However, the actual waveform itself is quite choppy and distorted. So typically what you'll see is a square wave with the switching waveform of a boost converter. However, mine is not very clean at all. So this could be for a couple of reasons. This could be the way that I laid out the converter itself. It could be the actual inductance. I have to double check again what the self-resonance frequency of that was and the overall frequency range of it was. And it could also be the fact that the output voltage is tied to a breadboard here, which can also induce noise in the system, as a breadboard circuit will always have more noise and issues than a printed circuit board, assuming that the layout was done correctly. I mean, the actual printed board circuit itself should be fine for the most part, given that the ground plane was clear. I tried to keep components as close as possible, along with using copper pores. But again, there could have been something that I was missing. This is the original board that came from JCLPCB. They didn't have all the parts through LCSC, so some of it I just hand soldered on. And I'll provide links for the parts that I had to hand solder on, such as the LDL regulator and the resistor book that I use for the different resistor values, along with the pin headers for the jumpers and the pin headers for the breadboard itself. Now, unfortunately, I can't really do more tests for this involving different loads and really pushing the boost converter and LDO to its absolute limit to see if it could actually withstand the given voltage and current ranges that we calculated. However, this is a good indication with that waveform to see, how my converter is performing in terms of stability and overall resilience. So I think there's definitely improvements that I could have made here. But given the fact this is already the third iteration, and I'm not exactly trying to put this on the market, I just want to use this for future projects, I think this was a step in the right direction in terms of analog hardware and design. As always, thank you for the support that I've been receiving on this channel. Here you'll find all sorts of videos regarding previous projects I did and the criticisms I had towards them, firmware videos, setting up microcontrollers, and tips and tricks for PCB software along with analog hardware, which is what I'm starting to do now. So as always, thank you all for watching and have a great day.